me and my grandfather. He gave me the Observer's Guide to Astronomy, and that was how I started going. Um, After 30 years in the UK, I was transferred across the Atlantic Ocean to General Dynamics in Ottawa, in Canada. I think you probably all know where Ottawa is. And after 5 years there, I moved out west to Calgary, which is in Western Canada. And I was there for a good 10 or 15 years. Uh, and then I was transferred again in 2003 by Harris RF down here, or close to here anyway, in Rochester, where I've been for the last 20 years or so. So my background is in engineering, defense systems engineering, and retired 5 years ago. Um, I've maintained an interest in astronomy my entire life, being member of the Astronomy Club in the UK, in Canada, and here in Rochester. So that's my background. Um, Quantum mechanics, I, it's kind of difficult. Uh, the whole thing is kind of difficult, but it's a very interesting topic. Um, the first thing you need to know about quantum mechanics is that it focuses on very small parts of the universe. It's not interested in the expansion of the universe very much. It's not looking at the way that galaxies are formed and all this sort of stuff. It's really looking at very, 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 very small parts of our universe. So let's move on. I'm going to be talking a bit about the history of quantum mechanics. We're going to be talking about some of the main or many players. There will be an overview of quantum mechanics, and I'm going to try and identify and discuss the main applications for quantum mechanics in astronomy and beyond. This is probably going to be way too much to get through in 1 hour. So we'll see how far I get going in 1 hour, um, and then we'll probably stop at that point, and we'll think about whether or not we want to continue at some point in the future. So Niels Bohr. Niels Bohr is going to be one of the people I'm going to be talking about. He was one of the major contributors to the theory of quantum mechanics. You may or may not have heard of him. And he said, well, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So that's where we're kind of coming from. Everybody's in a state of shock and nobody seems to really understand it all. Uh, and it's a very interesting story. So let's start off with wishing quantum mechanics is happy birthday. The year 2025, last year, marked the 100th anniversary of quantum mechanics. The theory describes the world at very small scales. As I already said, we're only talking about very, 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 very small scales down at the atomic level. And it's also famously counterintuitive. What it predicts, people throw their arms up and say, "Oh, this can't possibly be right." At its core, it suggests that the world is fundamentally random, that the world is not predictable. So, for example, two particles, two atomic particles, can be in several places at once. and they can be mysteriously linked even when they are very far apart. These are things that we might say is not really possible, but they're there. They're clear as day in the mathematics that describes the theory, and they've also been confirmed by many experiments over the years. So this is Schrodinger's cat. We'll be talking about Schrodinger's cat a bit later on in one of the thought experiments that are very popular in quantum mechanics. So the whole thing's been around for 100 years, um, and it's made a lot of progress in that time. Okay, so a little bit of introduction there. So it has it's confusing. It has what we would say are wave-like particles and particle-like waves. Quantum mechanics challenges our intuitions of how the world works. Much of what it much of what it says is counterintuitive to us, whilst driving to learn more, of course, is a very important part of science. When you zoom in on matter at the quantum scale, nature becomes very granular, or at least that's what we believe. At the scale, we find very tiny particles, such as photons. These are the particles of light that have no mass and no charge. There's also electrons, subatomic particles that make up the atom, carry electricity, and also have charge and mass. And quarks, these are building blocks, protons and neutrons. These are all parts of the building block of our atoms. In some ways, alternatively, you can think of matter as a digital image. If you zoom in enough on an image, you start to see it's made of individual pixels. Just another way of thinking about it. The lack of clarity in quantum mechanics create some unique behaviors. The consequences of these behaviors perplex the physicists who were the first to try to understand these behaviors. So these are the main things that we're going to be discussing in this discussion. The first of which is wave-particle duality. Tiny particles look like they are behaving like ocean waves. And it depends on how you observe them. Here we go. That's better. Superposition. Superposition is, in the quantum world, particles can exist in multiple states at once. If you think about a current computer system where a binary digit, a bit, can be either a 0 or a 1, in the quantum world, they can be 0 and 1 simultaneously. And that underlies the new quantum computing systems that are just beginning to be built. Heisenberg, the Heisenberg uncertainty principle. Heisenberg, we'll be talking about him a bit later. Nature imposes a fundamental limit on how precisely you can measure something. You can't measure certain pairs of properties at the same time with unlimited precision. We'll talk about this in a bit more detail, but basically, there's a certain limit to which you can actually measure things to a certain degree. Entanglement. Entanglement is a capability that allows two things that can be interconnected, that they influence each other regardless of distances apart. So two things can communicate, from a galaxy to another galaxy, apparently in 0 time. This does, of course, go against some of the other thinkings of our standard approach approach to the universe. But again, entanglement, as you'll see a bit later on, is something that we have tested and which we do actually use in quantum computing. And spin is a fundamental characteristic of all elementary particles, like mass or charge. Spin determines a particle's behavior and interaction with other particles. Okay, so in the 20th century, we really have two pillars. There was relativity and there was quantum mechanics. So general relativity, as you're probably aware, is what we could refer to as a compact jewel. It was conceived by a single mind, and I'm sure you all know that that single mind was Einstein. Based upon combining previous theories, it is a simple and coherent vision of gravity, space, and time. So we're not going to spend a lot of time talking about general relativity. Many people are aware of it and what it means, and we don't really discuss here the special relativity because it's slightly different in its approach. It came before general relativity. Because general relativity provides the curvature of space-time, which wasn't handled by special relativity. But that was a very big and important development that came, roughly the same time as quantum mechanics was being developed. Quantum mechanics, meanwhile, emerged from experiment in the course of a large gestation over a quarter of a century, from 1900 to about 1925. That was the period when it was all developed and where most of the work took place. Many, many people contributed to this quantum mechanics development, as opposed to relativity, which was really just the work of Einstein. What we have found, though, with quantum mechanics is that it has achieved unequaled experimental success. That is to say that every time somebody has come up with an experiment, and Einstein was always throwing out experiments or suggestions of things you could do. He just didn't want to believe that quantum mechanics was really genuine or not. But all of the experiments that have taken place over the years have indicated that quantum mechanics is correct. And it has led to applications that have transformed our everyday lives, such as the computer, and many other things as well over this time. But now here we are. We're more than a century after its birth, but it continues. Quantum mechanics continues to be shrouded in obscurity and incomprehensibility. As you're probably already thinking, what is going on here? It is a very complicated and difficult thing to get your mind around. But hopefully, in our hour together, we'll be able to learn a little bit of something about it. Okay, going back a little bit in time, Democritus, circa 460 to circa 370 BC, he was an ancient Greek pre-Socratic philosopher, Abdera in ancient Greece, and he formulated the atomic theory of the universe, the first atomic theory of the universe. Key principles of Democritus is atomism, atoms and the void. Fundamental realities are atoms and the void. Everything else is a temporary aggregation of atoms. Indivisible and eternal. Atoms are solid, homogeneous, unchangeable, and indestructible. Motion. Atoms are in a constant random motion. Variety. Atoms differ in size, shape, and arrangement, explaining the diversity of matter. And change. Perceived changes like colors, tastes are due to atom interactions, not inherent properties with images of atoms sloughing off bodies, blah, 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 blah. So this is a very early, obviously a very early theory, but it kind of brought the atomic uh, uh, theory into the life, you know. It gave it. So, getting rid of my phone here now, sorry. Uh, okay, move on from that one. Galileo, again, going through some history here. Galileo Galilei. So he was an Italian astronomer, physicist, engineer, often described as a polymath, born in the city of Pisa in Italy. It was then part of the Duchy of Florence. Um, Galileo has been called the father of observational astronomy, also the father of modern era classical physics, the scientific method, and modern science. He studied speed and velocity, gravity and free fall, the principle of relativity, not to be confused with Einstein's relativity, but just the relativity of things like inertia and projectile motion. And he also worked in applied sciences and technology, describing the properties of the pendulum, for example, and hydrostatic balances. He was one of the earliest Renaissance developers of the thermoscope, which was an early version of the thermometer, and the inventor of various military compasses. With an improved telescope, he built and observed the stars of the Milky Way, the phases of the planet Venus, the four largest satellites of Jupiter, which I'm sure you're all familiar with, Saturn's rings, lunar craters, and sunspots. And he also built an early microscope. Pretty busy guy. He championed the Copernican, the Copernican heliocentrism uh, theory. Back in his days, of course, the Earth was the center of the universe, but Copernicus came along and said, actually, I think the sun's at the center of the solar system. Um, but he was met with opposition from within the Catholic Church and from some astronomers, and I believe he was actually attacked by the Catholic Church. So one of his famous equations here, distance traveled by an object falling for time t, d equals a half of gt squared, where g is the gravity, the Earth's gravity, 9.807 meters per second squared. A simple equation, but one that's been around for a long time and tested many, many times. Moving on from him, Isaac Newton. Calculus is the mathematical study of continuous change. Um, and he was the original developer of calculus, an advanced branch of maths that deals mostly with rates of change and with problems such as determining areas or volumes within curved lines or surfaces. There was another German mathematician, Leibniz, Dr. Wilhelm Leibniz, who actually also independently developed the idea of calculus. But it's apparently well established that Newton developed calculus before Leibniz. But they were both eventually, I think, given the appropriate acknowledgement of their work. So now calculus is a basic entry point for anyone wishing to study physics, chemistry, biology, economics, or finance. I'm not going to be talking about calculus in any detail, but it is, as I said earlier, the mathematical study of continuous change, and Isaac Newton developed that approach. Then he went on, of course, he worked a lot with light and optics. Newton started his research into optics for the study of light and the behavior of light when he was a university student. And he took a prism and with a light in a series of experiments, he studied the spectrum of light projected onto a wall. His analysis pointed to the existence of individual rays of light that refract at different angles, as we can see in the drawing to the left. And of course, these results in phenomena such as rainbows going when rather than the glass prism is there, if it's a drop of water, it's raining. That's how we get our prism-like results. So believing that chromatic aberration or color distortion would always be present in glass lenses, he built the first ever reflecting telescope. His improved reflecting telescope and his theory of colors impressed the Royal Society in 1671-72, and he published his analysis in the book Optics. His observations of the fundamental nature of light have been foundational in modern science. And then his work with gravity. He analyzed planetary motion and universal gravitation. He proposed that planetary orbits are mostly elliptical because of the sun's gravitation. In 1684, the British astronomer Edmund Halley visited Newton with questions about orbital dynamics. Newton collected his findings for Halley in a book called On Motion, which he then started to improve and expand upon. And eventually Isaac Newton, it grew into his Principia Mathematica, mathematical principles of natural philosophy, which is the fundamental work for the whole of modern science in many cases. The Principia contains the law of universal gravitation and the three Newtonian laws of motion. So the initial equation for universal gravitation takes the form of F equals G m1 m2 over r squared, or F is the gravitational force acting between two objects, m1 and m2, are the masses of the two objects. R is the distance between the centers of the mass, and G is the gravitational constant, 6.674 times 10 to the minus 11. It's a pretty small number, but it's an inverse law. So when you move twice as far away, you get 1/4 of the amount of gravitational attraction. You work with gravity. The law of universal gravitation states that every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers, as we just mentioned previously. But then he went on to come up with these laws of motion. The first Newtonian law of motion is the principle of inertia, which states a body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. And I think most of you are probably aware of these laws. The second law states that the change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. And the third law states that for every action, there is an equal and opposite reaction. These principles are the groundwork for all the modern understanding of movement and physics. F equals ma, another famous equation, where F is the force, the net force acting on the object measured in newtons, units of newtons. M is the mass of the object in kilograms, and A is the acceleration, measured in meters per second squared. There we go. features of classical mechanics. So classical mechanics, not to be confused with quantum mechanics, classical mechanics predict a precise trajectory for a particle. And we can see this particle here moving along. It's got a velocity of v, it's got a position r, which is in three-dimensional space, an x, a y, and a z, or z. The exact position r and velocity v, and hence the momentum, because the momentum is p, which is m times v, which is position and velocity of a particle of mass m, can be known simultaneously at each point in time. Noting that position r and velocity v and momentum p are vectors having magnitude and direction. So this was the classical approach before QM, quantum mechanics, came along. So what then is quantum mechanics? That's a very good question. Quantum mechanics is a set of mathematical rules that describe quantum phenomena. Many phenomena observed in nature cannot be explained using classic mechanics. There's the ultraviolet catastrophe, and we can discuss that a bit later in this presentation if we have enough time. If you have an ideal black body, then a black body is an idealized physical body that absorbs all incident electromagnetic radiation, regardless of the frequency or the angle of incidence. So these idealized black bodies at thermal equilibrium would emit an unbounded quantity of energy at wavelength decreased as wavelength was decreased into the ultraviolet range. It's a bit of a mouthful now, but a bit later I have some better diagrams to show it. But that was a problem. This ultraviolet catastrophe was a real big problem, which was solved by Planck. Be easy. Here we're going again. There's Planck. Planck, one of the German guys solved the ultraviolet catastrophe problem by assuming that energy was not continuously divisible, as we expect, but rather that it comes in discrete packets. By treating energy as a discrete quantity, Planck was able to arrive at a model which perfectly describes the radiance of a black body. So that solved a huge problem. In that the problem with the ultraviolet catastrophe could be solved with these discrete packets, which eventually became known as quanta. And that's where quantum mechanics kind of started from. So continuing on a little bit. So what then is quantum mechanics? Quantum mechanics is the theory that describes the behavior of microscopic systems. So we're just talking about the very, 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 very small sizes of things, such as photons, electrons, atoms, molecules, etc. We're not talking about galaxies. We're not talking about solar systems. We're not talking about planets. We're not talking about two pieces of rock. We're talking about electrons and atoms and the very, 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 very small bits and pieces that we believe that our entire universe is built upon. I'm just going to mention Richard Feynman. We'll talk about him a bit more later. He was a well-known American quantum mechanics expert. And when he was teaching, he said, no, you're not going to be able to understand it. You see, my physics students don't understand it either. That is because I don't understand it. Nobody does. The theory of quantum electrodynamics describes nature as absurd from the point of view of common sense, and it agrees fully with an experiment. So I hope you can accept nature as she is absurd. You'll come across this type of comment from a lot of the main players in the quantum mechanics world. Um, because people just seem to feel that the whole thing is crazy. But there have been so many experiments now over a period of over 100 years that now we think that it's not a bad theory. Problems to be fixed. Toward the end of the 19th century, people thought that physics was done and dusted. Everything was sorted out. We had a whole bunch of elegant theories that described all the natural phenomenon people had observed, and that there's only just a few minor details that needed to be tidied up. Over the next few days, though, decade, alarming cracks started to appear, to open up in the theory. We just talked briefly before about the ultraviolet catastrophe, for example. And observations that were taken at the time showed that when examined at very small scale, nature just didn't behave as people thought it should. So quantum mechanics kind of came along and was developed to explain this newly emerging picture of the universe at very, 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 very small scales. Another interesting character, James Clerk Maxwell. So Maxwell's contributions were in the electromagnetic wave theory, which posits that changing electrical and magnetic fields generate each other. One generates the other generates the other. They propagate through space as self-sustaining waves at the speed of light. And by doing that, we can unify electricity, magnetism, and light itself. So that was where he was coming from in his proposal. So these are transverse waves. They're 90 degrees, or so to speak, that separate them. They feature oscillating electric and magnetic fields perpendicular to each other and the direction of travel, forming the electromagnetic spectrum, such as radio waves, light waves, X-rays, etc., etc. His theory is based on his four equations, so I won't go into the details here. And it predicts that light is an electromagnetic wave, and that these waves carry energy. So we can see there and here, we have an electric field, we have a direction, and we have a magnetic field. So that was what he put forward. Another quote here from Richard Feynman, which applies, I think, from a long view of the history of mankind, seen from, say, 10,000 years from now. There can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. So clearly, a very, very popular and famous and well-educated man like Feynman had such a lot of good things to say about Maxwell. So good news for Maxwell, huh? Faraday. Maxwell worked very closely with Faraday. Pardon me. Faraday is another experimentalist, and he discovered in 1831 that a changing magnetic field can induce a current. He performed a series of experiments that showed clearly that the induced EMF is equal to the rate of change of the magnetic flux. He also generalized from the patterns formed by iron filings around magnets. And you've probably all seen this at school, I'm sure, in the past. He invented the concepts of magnetic and electric field lines. He himself knew little mathematics and found this concrete approach to electricity and magnetism much more useful than equations given the forces between charges or currents. He also suggested that propagation of light through space consisted of vibrations of these lines. His concepts of electric and magnetic fields were put into mathematical form a generation later by Maxwell, who showed that light, in fact, is an oscillatory electromagnetic disturbance. But he was a brilliant experimentalist. He worked very closely with Maxwell. Maxwell was the brains, and Faraday had the hands to do the experimental work. The two of them worked very closely together. James Clerk Maxwell was Scottish. He came from a very wealthy family, and Faraday was a very poor guy from London. So just to for a little bit about the electromagnetic spectrum, as I'm sure most of you know, we have gamma rays, we have X-rays, we have ultraviolet, we have the visible light, we have infrared rays, radar waves, microwaves, television waves, and radio waves, all of which have different frequencies and different wavelengths and different photon energies as well. The electromagnetic spectrum is the entire distribution of electromagnetic radiation according to frequency or wavelength. Although all electromagnetic waves travel at the speed of light in vacuum, they do so at a wide range of frequencies, wavelengths, and photon energies, as you can see in the complicated diagram here. The electromagnetic spectrum comprises the span of all electromagnetic radiation and consists of many subranges, sometimes referred to as portions, such as visible light or ultraviolet. The portions bear different names based on differences in behavior. Another characteristic, there is no precise accepted boundaries between any of these contiguous portions, so the ranges tend to overlap. Some of this we've already talked about a little bit. By the middle of the 19th century, the experimentalists, including Faraday, had established clear evidence for the connection. They had shown, for example, that electric currents can generate magnetic fields and that moving magnets can generate electric currents. The equations also enable Maxwell to calculate how fast electromagnetic waves travel through empty space, and to answer thereby a question people had been contemplating for a long time. It was known at that time that light travels very, very fast, but does not travel infinitely quick. It does take some time for light to get from point A to point B. And there had been some various experiments that had measured this. But one of the most remarkable eureka moments in scientific history was when Maxwell sat down, or so it is said, and calculated from his equations the speed of light and got the right answer. And the answer was speed of light is 299,792 and 458 meters per second. Quite the achievement back in those days. The result was encouraging, but it took another 25 years until the physical existence of the waves predicted by Maxwell were proven in experiments. Hertz, you may have heard of Hertz. He demonstrated the physical reality of these waves by generating an oscillating electric current and then picking up a signal corresponding to what we would now talk about as a radio waves in a receiver. He did that in the lab. Hertz did that in the lab. So perhaps you might say it was a bit of a curiosity. Along comes Marconi, and he showed that you could actually send radio waves across the Atlantic, which I believe was from the southwest corner of the United Kingdom to Newfoundland in eastern Canada. The Marconi's radio waves certainly made life a lot easier to keep in touch around the world, and that revolutionized the way that human beings communicate. And it all goes back to Maxwell's equations. So Mr. Maxwell's another smart guy. Ernest Rutherford is another interesting person. He's Baron Rutherford of Nelson. He was a New Zealand physicist and a pioneering researcher in both atomic and nuclear physics. He's also been described as the father of nuclear physics and the greatest experimentalist since Michael Faraday. And you can see he came up with this, they have the nucleus of the atom, and then electrons going around in little orbits around the atoms. And he used alpha particles going through some gold foil. So he was very much into defining or helping to define the early thinking about the structure of the of the atom. In 1908, he was awarded the Nobel Prize in Chemistry for his investigations into the disintegration of the elements and the chemistry of radioactive substances. He was the first oceanic Nobel laureate from the Pacific Ocean, and he was the first to perform Nobel awardee work in Canada. Okay, so through a little bit of the history now. So 1900 was Max Planck quantum hypothesis. 1905, Albert Einstein comes along with the photoelectric effect. 1913, Niels Bohr and Bohr's atomic model. 1927, Werner Heisenberg and the uncertainty principle. 1932, John von Neumann, mathematical foundations of quantum mechanics. 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen, the EPR paradox. And 1964, John Bell's theorem. I don't plan on spending we don't have a lot of time to get into the more recent stuff. So we're going to be focusing on the earlier parts of this from 1900 to 1927. See how we get on time-wise. As we discussed earlier, most of the work took place between 1900 and 1920, 1930, thereabouts. And then a lot of other work has occurred in the meantime. But the earliest period was the most productive and exciting. So I'm going to skip over John Stuart Bell because this is a relatively recent development. So let's talk a little more about some of the quantum mechanic players. So they had a meeting, all the exciting people, they all had a meeting once a year in the early 1900s. This is the 1927 meeting. This is the fifth conference. Solve, I think, I'm not sure if Solve was the name of the town or whether it was the name of the beautiful building where they held it, but they used to have these meetings. And there's a big gathering here. We have Albert, you'll all recognize Albert Einstein on the front row in the middle. Niels Bohr, here is Niels Bohr hiding over here in the corner from Denmark. Erwin Schrödinger, Austria, here he is at the back with his beautiful red tie. We have Marie Curie, she's the only lady there. Max Planck, who's sitting right next to Marie, and Paul Dirac. Here is Paul Dirac, who's actually British, one of the few. And there were many more people that came afterwards, as you know. I've already mentioned briefly Richard Feynman, John von Neumann, John Stuart Bell, and J. Robert Oppenheimer. So what did Albert do that helped us in quantum theory? Well, he's better known, of course, for the theory of relativity, particularly the spectral and general. He revolutionized the understanding of space-time gravity in the universe. E equals mc squared. We all know this one, I think. The famous mass energy equivalence formula, the cornerstone of modern physics. It's the reason we have the atomic bomb, unfortunately. And it certainly kept him busy. The photoelectric effect. So the photoelectric effect is the emission of electrons from a material pulled by electromagnetic radiation, such as ultraviolet light. Electrons that are emitted in this manner are called photoelectrons. He proposed, that is, Einstein proposed that light as particles, photons. And this paper that he put together in 1921 got him the Nobel Prize in Physics. That was the same year that he poured his special and general relativity papers. There were 3 papers in that year. The Annus Mirabilis. But the relativity was too difficult, I think, for the Nobel people to come to terms with. So they said, "Oh, this photoelectric thing looked much easier and to understand, so we'll give him the Nobel Prize for that." The light color, the frequency, and not the intensity determines if the photoelectric effect happens. The light color, that is to say, its frequency, and not its intensity determines if the photoelectric effect happens. And some substances generate a weak electric current that emit electrons when light shines on them. Quantum theory. So he contributed significantly to quantum mechanics, explaining light particle nature. Brownian motion. He provided proof of the existence of atoms and molecules. Bose-Einstein statistic is a new state of matter. Modern physics. His impact and legacy, his theories form 2 pillars of modern physics, special relativity and general relativity. Lasers and solar cells are all based upon his work. Cosmology, he predicted black holes, gravitational waves, and the expanding universe. I already mentioned 1905, the Annus Mirabilis, his miracle year, when we saw the publication of his most influential papers, photoelectric effects, special relativity, and general relativity. And then quantum mechanics to comprehend how light may be simultaneously an electromagnetic wave and a swarm of photons kickstart quantum mechanics. The first building block had been established. There exists a fundamental granularity in all things, including light. So that's a very important point. the fundamental granularity in all things. Here's a quote from Mr. Einstein: I know not with what weapons World War III will be fought, but World War IV will be fought with sticks and stones. So what is the world made of? So back in the time of Newton, we had space, time, and particles. When Faraday and Maxwell came along, we still had space and time, but particles had been kind of made into particles and fields, electric fields, magnetic fields. When we got to Einstein's special relativity in 1905, space and time were kind of together. I mean, he came up with this whole thing about space-time and how they were very, very closely related. Fields and particles stayed where they were. And then general relativity, which brought in the whole gravitational thing, we went back to fields again and particles. Okay, let's move on to another one of the major people in this great story. This is Dirac, Paul Adrien Maurice Dirac. His father was French. Father had moved to England, and Paul was born in England. He had a very poor relationship with his father. His father insisted that he speak French, and he didn't want to speak French. He wanted to speak English. So they had a bit of a fight about that. Paul became very quiet and stayed that way for the remainder of his life. He was very, very quiet. Niels Bohr, that we've talked about, said of Dirac, of all physicists, Dirac has the purest soul. He developed Dirac developed the surprise, the Dirac equation, which is a fundamental relativistic wave equation that unifies quantum mechanics and special relativity, describing particles like electrons. He predicted antimatter like positrons and incorporated particle spin naturally. He reckoned or his work reconciles how particles behave at high speeds with quantum rules, explains the hydrogen atom's fine structure, and forms the basis for modern quantum field theory. Introducing concepts like spinors that we don't really have time to talk about, other than the fact they're variations on Euclidean space, and leading eventually to the what they call the standard model, which was the kind of the baseline for all of this work. What's his quote here? Pick a flower on Earth and you move the farthest star. The standard model is just briefly whilst we're here. It's the modern physical understanding of the three of the forces of nature. And the standard model covers electromagnetism, the strong nuclear force, and the weak nuclear force. And you can see here the atoms, they have a probability distribution of the electrons. The core, the nucleus of the atoms break down into neutrons and protons. And then each of these neutrons and protons break down into different types of quarks. This rather large table here shows our current thinking about the structure of the atom, and we've got 24, 29 different elementary particles in the standard model. It's the most complete description of the subatomic world that's ever been created. That's obvious. The model was built through the 20th century on the foundation of quantum mechanics. the strange theory that describes how particles behave at the tiniest scales. That model explains three of the four forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. The theory has been tested thousands of times, and seems to be pretty stable. The big CERN accelerator in Geneva, in Switzerland, is used to do all of this work. So you can think of it as matter. The matter is made out of quarks and leptons. Force carrier is made of bosons, and the Higgs is made out of provides mass. The Higgs is a fairly recent discovery. Unified Dirac, he unified quantum mechanics with special relativity and predicted antimatter. He created the bracket notation. We don't have time to talk about this, but the bracket notation is what we now use, or what will be used now, for quantum computing and writing their code. He laid out the groundwork for quantum field theory and quantum electrodynamics, and he was given the 1933 Nobel Prize. You'll see nearly all of these people eventually ended up with the Nobel Prize. Einstein, Dirac, all of them, pretty much. We move on to Werner Heisenberg. So his key contributions were the uncertainty principle. So he postulated that for conjugate variables like position and momentum, or energy and time, greater precision in measuring one of those inherently means less precision in measuring the other. So the uncertainty principle states that you can't know all the information about everything. There's a limit to how much information we can uncover from the quantum world. Matrix mechanics, he was heavily into the mechanics of matrix mathematics, along with Max Born and Pascal Jordan. And Werner Heisenberg, is another, earned the Nobel Prize in 1932. Another one of them gets the Nobel Prize. His comment here is, what we observe is not nature itself, but nature exposed to our method of questioning. Here's a picture of him, looking very serious. The uncertainty principle, also known as Heisenberg's indeterminacy principle, is a fundamental concept in quantum mechanics. It states that there is a limit to the precision with which certain pairs of physical properties, and we've talked about this briefly, such as position and momentum, can be simultaneously known. Or to put it in another way, one property is measured, more accurately one property is measured, the less accurately the other property can be known. More formally, the uncertainty principle is any of a variety of mathematical inequalities asserting a fundamental limit to the product of the accuracy of certain related pairs of measurements on a quantum system, such as position and momentum. I know that's a mouthful, but basically, we can't know with any great detail both of these measurement properties. We can only know one of them. And as one of them gets to be known more and more accurately, the other one gets to be known less accurately. This is the uncertainty principle. And this is one of the core principles of quantum mechanics. Here's the uncertainty principle equation. The uncertainty in position multiplied by the uncertainty of momentum, for an example here, has to be greater than or equal to Planck constant Planck's constant is a very, 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 very small number divided by 4 pi. So, for example, delta P is the uncertainty in position, delta X is the uncertainty in momentum. So delta P times delta X signifies that the uncertainties in position and momentum are inversely related. The more accurately we know one, the less we know the other. So that is the uncertainty principle. Niels Bohr. So Bohr, Bohr developed the Bohr model of the atom, in which he proposed that energy levels of electrons are discrete. So previously we thought that we had the nucleus and we had the electrons, and the electrons were just all going around in a kind of random cloud around the atom. What he proposed and what we found to be the case is that the atoms can only be within certain orbits, and when they move between orbits, they move like in a quantum manner between those orbits. They don't slowly kind of like a satellite in orbit. They don't slowly slow down and then enter the atmosphere. They just kind of jump from a higher level to a lower level, or vice versa, from a lower level to a higher level. And he proposed that the energy levels of electrons are discrete in that the electrons revolve in stable orbits around the atomic nucleus, but can jump from one energy level to another. Uh, uh, he uh, he was in Denmark, Copenhagen, during the Second World War. He's a Dutch guy, Danish guy. During the war, he lived in the UK, and he visited the US quite often during the Second World War, and contributed to the Manhattan Project. And you see his comment: "An expert is a man who has made all the mistakes which can be made in a narrow field." So here's the model of the atom. You got the core of the atom, the nucleus. There are these orbits, like the first orbit, the second orbit, the third orbit, and the electrons can only jump up or down between those orbits. So this is another quantum thing. They're not in continuous orbits around the nucleus. The electrons are only enabled to jump between these discrete orbits. When an electron loses energy, it doesn't gradually inch inwards towards the nucleus, but performs a leap, quantum jump, to the next allowed distance. When it reaches the smallest allowed distance, which would be this little n equals 1, it can't go any nearer to the nucleus and stays where it is. Bohr's model had another advantage. It explained the discrete spectrum of the hydrogen atom, which had hitherto puzzled people. We don't really have time to go into the details, but there was a lot of support for what was proposed in the quantum models. And they were one of the things I found most interesting about studying these people is there's a lot of human interest. Although they used to fight a lot, these people about their ideas, they were also very good friends. Niels Bohr was always fighting with Einstein, but when Einstein passed away on April the 18th, 1955, Niels Bohr wrote a tribute to him in the newspaper, which was sent to the scientific community and Einstein's family. With the death of Albert Einstein, a life in the service of science and humanity, which was as rich and fruitful as any in the whole history of our culture, has come to an end. Mankind will always be indebted to Einstein for the removal of the obstacles to our outlook, which were involved in the primitive notions of absolute space and time. And when Niels Bohr himself passed away a few years later, somebody took a photograph of the blackboard in his study. And there's a drawing there of the box of light. Box of light is one of Einstein. Einstein was always throwing up ideas, experiments, thought experiments to try and prove that the quantum guys were wrong, right? Particularly Bohr, because Bohr was the guy who really drove the quantum thing. Um, so there we go. There we see. There we see. Even towards the end of his life, he was still working on it on his board to the very last. The desire to debate, to understand more, to the very last doubt, and this permanent doubt of the deep source science at our time. 38. So would this be a good place to stop, or would you like me to continue on for a little bit?
What do you guys think? Do you,
I think it's a good place to stop.
yeah, I think you've given us a lot to think about already. And if you can come back in the next few months, kind of just
Okay,
briefly reprise this and then finish off, that'd be great.
okay. So we'll stop at Irwin, one of my favorites. He's a naughty boy, this guy.
This is
Yeah,
great history. This is awesome, Adrian.
I'm
So
glad.
thank you very much. I really
I'm,
enjoy
glad-
this.
I'm glad you enjoyed it.
Any other
Well,
thoughts or questions?
It's been very good. I've enjoyed it also.
Are the slides going to be available?
yeah, sure. If you let me know, and I can send you a copy.
And then we'll make this recording available on the website as well.
Awesome. Thank you, Craig.
Let me stop the recording.